Agwene Korja is Misha Paula Quinigon. Welcome back to the second afternoon of IST-Africa 2022. Following two excellent keynote presentations, we're now starting our third eHealth session. And that's going to start with GenoTrack, a web tool to spatially link bacterial genomes from environmental and clinical settings.
Good morning, good afternoon, or good evening, everyone. I'm Deogratias Ekwanzala, a postdoctoral researcher at the University of Gothenburg, Sweden. I'm a qualified biotechnologist and an experienced microbiologist. I have worked in South Africa, South Korea, and currently in Sweden. The project I will present to you today was part of my PhD at the Tshwane University of Technology, which was supervised by Prof. Malimumbo. So the current tool idea was birthed after the 2017-2018 Listeria outbreak. So to put you into perspectives, is that the first case from Steve Biko Hospital was reported to the NICD in July 2017. However, the causative agent and its source, which was the polony, a sausage, could only be revealed after 9 months on the 4th of March 2018. Unfortunately, during that time, during that period, about 937 cases was reported and about 216 people died from the infection. Consequently, we ask ourselves if there is any way to shorten the time taken to identify the source of this organism, organisms that are coming from the environment, by creating a tool that can geospatially link environmental, meaning food and water, to clinical setting. Hence, I'm presenting to you the GenoTrack. So, environment-related infection, including waterborne and including food and waterborne bacterial pathogens, are a significant cause of mortality in developing countries and cause substantial morbidity in developed nations. According to the WHO, foodborne diseases cause morbidity in about 600 million people here, and approximately 420,000 people die every year as of that. This situation is aggravated with the current emergence of multi and pan-drug resistance, where their spread and development are no longer a potential risk only, but a genuine health risk that is rapidly expanding worldwide. There is therefore a need to monitor the movement of pathogens across the environment and the clinics. To remediate to this problem, different avenues are being explored, and one of them include the development and implementation of a surveillance system, right? So in the wake of the genomic technology as an integral part of the fourth industrial revolution in life science, the number of whole genome sequencing of clinically relevant bacterial genomes are on the rise. This provided for us an opportunity for improved surveillance on antibiotic-resistant bacterial genomes that links environmental and clinical settings. Consequently, a web tool was developed to fill the gap of this environmental nexus. This study, therefore, reports on the development of GenoTrack that spatially map human bacterial genome isolated from different environmental and clinical settings, focusing on the sequence type and antibiotic-resistant gene content, right? So how was the GenoTrack developed? GenoTrack is a Netcore Webtool application written in C++ and C# from the ASP.NET Core 2.2. The Netcore platform supports all the backend analysis of GenoTrack. Right? The SQL server was used for the management of the database. The front end of GenoTrack Webtool was built using Angular 8 framework, which uses D3 charts to generate dynamic and interactive data visualization in the GenoTrack Webtool browser. The interactive map was incorporated from Google Maps. The alignment for the phylogenetic tree and genome features were built based on the progressive mode alignment. The phylogenetic tree was implemented in the PhyloNode module, a molecular phylogenomic tool using Node.js. The comparison of genome was implemented in move charts, right? So this is the overview of the computational and pipeline implemented in GenoTrack Webtool. So in the top part, you will see that you have genomes that a user, the person that want to track a genome, will provide a genome genus, a genome species, strain, genome sequence type, isolated setting, specific source, isolated location, and also put in some antibiotic resistant genes if there is any. And all of this has to be provided in a gene bank format because it's rich and it contains all this information embedded, annotated already. Once it is provided, it goes into the SQL database, and from the database, similar genomes are pulled based on the genome species, right? And the first analysis that you're going to get is a geospatial mapping from Google Maps, where it shows how the distribution of genomes that you have provided and the ones that are also found in the similar genome that are also found in the database. After mapping that, there is an alignment part that is being done. And after the alignment, you're going to get the phylogenetic tree. And you're also going to get a genome feature based on move chart, right? So as I said, this is a web tool. So you have a landing page. So this is the landing page of GenoTrack. This page actually allows you to create, using the login, to create your own user profile, and then be able to upload genomes and track your own in the system, track your own genomes in the system, right? Create the project and all this. Once you have created and uploaded all the required attributes that you need to give to your genome, GenoTrack generates a map of a map showing your genomes how they're distributed on a map, which serve as the initial data. Basically, it's going to show you where the genomes are from, right? And after that, you're going to get, after the alignment has been done, and you're going to get the phylogenetic tree. The phylogenetic tree allow you to see how closely related your genome of interest is with the one that are already in the database. By doing this, you'll be able to identify clearly the source of the organism. Let's say we were tracking for one of this genome that we have here. So if, for example, we were looking at this genome, we will be able to know that the other one, if it's from a different environment, then we will go and look at it, right? After that, if you want to dive deeper and your genome have things in that you isolate have the more genomic attribute that you would want to look at. We also provided a MOV charts where you can actually look at those specific genomic. You look at, for example, if you have a antibiotic resistance in your genome of interest, you want to see if the same genome, the same antibiotic resistant genes is also in the other genomes that has been found in other places. This allows you to further confirm that the genome that you have is indeed coming from the source that you're looking at, right? So, to the best of our knowledge, in conclusion, to the best of our knowledge, this is the first Webtool of its kind to integrate both environmental and clinical genomes, to reveal niches and hotspots of pathogenic bacteria for epidemiological content action. GenoTrack is a free and public genomic epidemiology resource that enables tracking genomes in database using an interactive web tool and visualization. GenoTrack integrates three main computational analysis pipeline. Firstly, you have a genomic algorithm for geospatial mapping of genomes. Secondly, you have phylogenetic analysis using balanced minimum evolution implemented in philo.not of Node.js. And thirdly, you have a genome alignment using the algorithm implemented in progressive mode aligner. So we encourage we basically encourage the scientific community to add more genome and policy makers to use Webtool to formulate an appropriate strategy to contain the movement of clinically important bacteria. So further improvements on the Webtool should include incorporation of artificial intelligence, machine learning, and deep learning to automate the database recruitment of genomes and also analysis. In that, I would like to thank the NRF for funding our research units, the South African, the Sakiche in water quality and wastewater management, and also providing me with the funding during my PhD for NRF freestanding doctoral scholarship. And I would also like to, last but not least, I would also like to thank the developers, Judith Adomomba, Rito Vukela, and also Mr. Tulani Makuba. Thank you very much.
Thanks, Dio. This is very interesting work. Can you talk to us a little about how the integrity of data is protected? Where is it stored? And are there potential security or privacy related risks to this type of data and how it could be abused?
Oh, well, basically with the genomes, we don't really provide personal data. It is the user, I'm talking about the epidemiologist and the policymaker that are actually going to be logged in with their basic details. There's no, the genomes is not linked directly to the humans that are providing them. So there's no security problems with that, because the genomes that we're talking about is just bacterial genomes that we're talking about here.
No, I realize that. I was more looking at it from an anti-bioterrorism perspective and to prevent bad actors using data for purposes for which it was not intended.
Oh, well, we didn't look at it on that point, but the web tool itself will be hosted by the university, and it has a secure server. So I think having that stored in there, we will have less threats to data being leaked or anything like that.
Thank you. And then is the point that you're trying to create an open access repository where all of the data will be stored, or do you envisage that there could be different repositories using the software, but the backend be independent?
It was breaking. Can I?
Of course. No, it's no problem. So what I was wondering was, do you envisage that it will be an open access repository where anyone using it would use the same backend to store and analyze data? Or do you envisage that some people might use the tool and have their own private backend?
No, we will still be doing the backend work. So I think
Perfect. Okay.
we want people, to come here, not doing their own work. Yeah.
And who else are doing work like this that could be potential collaboration partners for you going forward?
Obviously, in the early development of the web tool, we had contact with the NICD, the National Institute of Communicable Diseases, that was really interested in the project. So we are already in collaboration with them, and then we're looking forward to using it for Africa and everything. So it's going to be a collaboration between the university, the Tshwane University of Technology, and directly with the NICD, going with the network of other laboratories to work together so that they can implement.
Yeah, no, that was what I was going to encourage, that you would look at it from a Pan-African perspective rather than a South African perspective, because I think that's where we would achieve most impact.
Yes. Thank you.
Thank you very much. Does anybody else have any questions or comments for Dio before we move on? In which case, Dio, I look forward to learning more about your work. So our next presenter is Raj, and the presentation is on next generation DNA sequencing technologies and implementation science in reducing the impact of familial colorectal cancers in developing countries.
Colleagues, the topic for my presentation today is next generation DNA sequencing and implementation science in reducing the impact of familial colorectal cancers in developing countries. To introduce myself, I head the Division of Human Genetics and the Department of Pathology at the University of Cape Town and the National Health Laboratory Services. The Department of Pathology at the University of Cape Town is comprised of 8 fairly large independent specialties, and they're listed in this departmental logo. The purpose of my job at the University of Cape Town is to design and produce education and training material for the next generation of pathologists. And more importantly, it is to produce the next generation of diagnostics for diseases in our populations towards improved therapeutics in this specific era of precision medicine. Colleagues, I'd also like to take this opportunity to draw your attention to this probably underappreciated but potentially phenomenal partnership between the National Health Laboratory Service, which is a component of the National Department of Health, and universities in terms of being a hotbed for innovations. And the specific aspects I'm drawing your attention to is the remarkable national footprint of the National Health Laboratory Service, which actually gathers vast amounts of data that are generated on a daily basis. This provides a really real means of getting a national trend of disease in real time, that is epidemiology. And it is also possible to track individual data in amongst this vast amount of data that we have access to. But today, my specific area of expertise that I'd like to bring to your attention is the field of genomics or human genetics. And this is human genetics on a grander scale. Colleagues, and what is probably well, important enough for me to emphasize here is at the core of genetics and genomics is the work we do in understanding the biology of the human species and what happens at the genetic level. However, on a grander scale, when we're talking about human diseases, we have developed technologies in human genomics to sequence vast amounts of genomic material, and this is the era of big data and genomics. So the human genome, and in practically every one of our cells, we have about 3.5 billion bits of genetic coding material. And if one is thinking about looking at, not even thinking about, well, we practically do look at genomics of individuals, and large numbers of individuals are studied at a time, one can appreciate the vast amounts of data we gather. And this is not too dissimilar in scale to the vast amounts of data that are being processed and analyzed in, for example, the amazing area of astronomy. And just bring it to your attention the work that is being done in Southern Africa on the square kilometer array. But sinking or holding both these very disparate areas together is the symbolic use of the hourglass. And at the cinched or waist area, we're talking about the overlap of big data. So big data, the science of big data, is really where we are playing a major role. And this falls slap bang in the middle of this entity we call the Fourth Industrial Revolution. And for us, it is specifically to do with healthcare. Colleagues, I further want to delve into talking about cancers specifically. And I'm convinced that the majority of you in this audience appreciate that cancers actually affect the genome. And there is no cancer that will develop without an insult or a mutation occurring in our genetic material. So the majority of these insults are due to environmental factors or extraneous factors acting on the genome, ultraviolet light, for example, bringing about mutations, and this results in cancer of one kind or another. However, the specific cancer that we're interested in is cancers that run in families. So this is familial cancers. You would have heard of breast ovarian cancer, for example, but the one that I emphasize here is colorectal cancers, where there's a clear pattern of inheritance, as is illustrated on the left-hand side of this particular slide, where you get the person right at the top, passing on a defective gene onto the next generation, and this is shaded in green, who in turn then passes it on to about 50% of the next generation of offspring. So, as we all know, cancer is a major disease burden affecting all communities and populations. What we know, and I'm sure you know, is that the earlier the diagnosis is made of practically all cancers, the greater the chance of a successful outcome. So it's not a surprise then that we focus on cancers which have a hereditary basis to identify the genetic basis of the disease, in which case, as soon as we identify a mutation we know that passes on from one generation to the next, causing havoc as it goes through, we're able to predict, for example, the next generation, as is apparent in this slide showing individuals who are affected in every generation. For those individuals who are not yet affected, we can actually do a genetic test and determine whether they're likely to have inherited the disease-causing mutation. So here's a practical slide of the work we do. So obviously, I mentioned we work on colorectal cancers. It's anywhere in the region of the colorectum. And understanding the genetic basis, as is illustrated here, in fact, clearly shows that there is a mutation in one of several potential genes. And if we know what that mutation is, clearly illustrated in this family tree on the right bottom, is the validation, i.e. showing that every affected individual is carrying the disease-causing mutation, in which case you can confidently go ahead and test all of the as yet unaffected individuals to determine whether they're likely to develop the disease or not. So, in brief, by way of brief explanation, what should be obvious is those individuals who have tested and come up negative are shaded in green and they're released from follow-up. Sir, ma'am, you do not have the mutation that has probably been plaguing you your whole life in terms of stress. You don't need to come in for colonoscopies. Whereas perhaps more importantly are those individuals in yellow who are tested and shown to be carrying the mutation, and they are very likely to develop colorectal cancer in their lifetimes. And interestingly, they develop a range of other cancers, but not as commonly as they develop colorectal cancer. So you can see the value of being able to identify these genetic factors. In this slide, we illustrate the major outcomes of this kind of testing. This is a survival curve, and on the x-axis you see age in years, and on the y-axis you see the proportion of individuals one is looking at in a community. On the left graph, what I'm illustrating are individuals in blue, siblings who do not carry the mutation. You can see they lead a normal long life, compared to their siblings or relatives in red, who in fact are carrying the mutation, and you can see their lifespan is compromised pretty severely. Now, moving on to the slide on the right-hand side, what I'm illustrating here are both sets of curves, in fact, pertain to individuals who are mutation positive. The blue curve indicates those individuals who are tested and counseled to come in for colonoscopic surveillance and adhere to this guide, whereas their relatives in red also tested for the mutation, but in fact are not compliant or do not come in for colonoscopies. And you can see there are dire consequences for these individuals. So, proceeding with our work on colorectal cancers, just to let you know that I talked about sporadic cancers of one kind or another, and they are by far, affect the majority of the population. However, hereditary cancers can affect about as high as 20% of all cancers. So our challenge is in identification using a range of clinical and pathological features of the disease and the tumor, but primarily using a family history to identify individuals who are likely to have hereditary colorectal cancer. This has been long recognized internationally, and we used criteria, about 3 decades ago, that were called Amsterdam criteria, Bethesda criteria, the Nice criteria, and in these we emphasized family history. However, what's happened in the last perhaps 5 to 10 years, the availability of next generation technologies and next generation DNA sequencing precisely, is that practically all individuals who are affected with, in this case, colorectal cancer, and here I refer to first world countries, are put through a panel of about 20 to 50 likely genes within which mutations are likely to cause disease. And this is at a cost of about between 7,000 to 10,000 rands per patient, with a 10% pickup rate. So that we cannot afford. So even though we have access to next generation sequencing, it is really not practical or budgetarily fair with regards to affording the whole population this kind of thing. So what we've come up with is a combination of good clinical acumen in devising a scoring model. And from the scoring model, i.e. assessing patients very carefully in a multidisciplinary team, to then, after sorting, to judiciously use next generation sequencing in terms of identifying the precise mutation. So here's what I'm talking about. On the left-hand panel, what you see is the multidisciplinary team, and this is sort of the pathway the patient would generally traverse through, i.e. consulting a surgeon, and then be referred to an oncologist. The tissue that may be excised from this individual during an operation will be sent to the anatomical pathologist, who then, depending on what is picked up there, would refer the patient to a geneticist. So what we're proposing is this rather simple but very effective model of where the moment a clinician identifies a patient with any feature that is perhaps reminiscent of a familial colorectal cancer, they would open this app on their phone, or at this stage it's just a worksheet actually, and start to score. If this patient has a family history, you give that individual a score, and then depending on where the tumor is located, whether it's on the ascending colon, transverse colon, or descending colon, you give a score. And then as the sample from the patient is processed through the anatomical pathology laboratory, there are various different histopathological tests that are done, and I've listed those here, this particular specimen is given a score. And it is through this kind of scoring system that one triages every single patient who has colorectal cancer, but it's only those individuals who meet a score, an arbitrary score at this stage of about 8 out of 10, who will then be processed and passed on to next generation sequencing. But obviously this is accompanied by genetic counseling to a great extent. And that individual's material, generally blood, is then subjected to next generation sequencing. So you can see here, instead of next generation sequencing being the be all and end all, it takes its place in being a reasonable fit in our environment, and where perhaps 10 to 20% of the patients we see will be processed through next generation sequencing. And in that instance, there is this clear workflow from the clinic through the scoring instrument and ultimately the application of genetic testing to identify what we talked about earlier, those individuals who are carrying the disease-causing mutation and those who are not. And I emphasize here, ladies and gentlemen, that importance of genetic counseling to accompany all of this work. So what we have is this working model in the background, and the way forward is, in fact, it's happening right now, is that we're developing a regression model where we're actually looking at all of the data we've gathered on the hundreds of patients in whom we already know have a genetic mutation and have either developed disease or likely to develop disease. And we're collecting all of the clinical data as well as the laboratory diagnostics for those individuals. And we're using that to calibrate each of the components of the scoring system. And this is to a less or greater extent using artificial intelligence, so the system learns to improve itself as we go along. And ultimately, and perhaps pretty soon, what we would have is an app for much wider availability. And this would then mean that you actually have your multidisciplinary team on your handheld device and would be available in rural environments to healthcare providers there who don't have the level of sophistication that we may have at tertiary and quaternary centers. It is then with this kind of scoring system, colleagues, that we would, arbitrarily screen all 100% of colorectal cancer patients we're likely to be seeing, and then subject them to scoring, and then enrich for those individuals who are very likely to have the disease-causing mutations, and ultimately to get this coming through the next generation sequencer and provide genetic testing and afford the families appropriate management in terms of reducing disease in those lineages. Importantly, what we're also developing at the moment, ladies and gentlemen, as you may know, we have in South Africa a National Cancer Register. What we have already proposed is we have a National Familial Cancer Register in which we have the individuals and families registered where we have mutations, which would then mean that regardless of where these individuals are in the country, they are actually afforded access and management through the genetic testing, genetic counseling, and clinical management system. So in conclusion, colleagues, what we could say is that we have previously demonstrated how to identify suspected individuals with familial colorectal cancers through a multidisciplinary team of professionals. We have developed an innovative disease scoring model for Lynch syndrome of familial colorectal cancers, which is being improved using artificial intelligence for accessibility and use by a wider range of health professionals. And this is to couple to the judicious use of expensive next generation sequencing technology to increase sensitivity and specificity. And this is coupled to the development of a National Familial Cancer Registry within the National Cancer Register, which is currently housed in the National Health Laboratory Service. And this will provide increased accessibility and utility of precision medicine in this era of big data. And ultimately, what we hope to prove with this kind of work is that we would have reduced morbidity and mortality from this group of disorders. Colleagues, I take this opportunity here to acknowledge IST-Africa, the funders, the South African Medical Research Council, the National Research Foundation, the Wellcome Trust, and Cancer, and also my home base, which is the University of Cape Town. Thank you very much.
Raj, thank you very much. I know that any family that's been impacted by cancer finds this both fascinating, frightening, and something to perhaps give them some hope for managing that risk in the future. I like the proposed approach of using the disease scoring model as a filter for the next generation sequencing. But how do you see that being operationalized? And how do you ensure that the places, rural and deep rural environments in particular, that most need something like this and are least likely to get that intervention at an early enough stage, start to adopt that type of app when it becomes available, to try to give people in those environments who may have a high risk better chance of surviving the experience?
Thanks very much. So look, this is a longer path that we're treading. So the work that we're doing right now started more or less 2 or 3 decades ago. So the harvesting of this is actually where we are with regards to applying the technologies. And speaking about getting to pretty much every corner of the country requires a combination of education and training of health professionals, and we have various means of doing this, but also the reach of the National Health Laboratory Service, which is actually quite vast. So it's using these, and obviously publicity and the interest in developing precision medicine as a national instrument is our proposal to get through to the community.
Just to follow up on that, Raj, one of the earlier presentations today was talking about the stigma of diabetes in Mauritius, which I found, as an island nation, coming from an island nation, Ireland myself, I found it interesting that there are many things to have stigmas about, but the last thing you would have a stigma about in Ireland, for example, was diabetes. But obviously, different countries have different cultures. But obviously, with something where people may have symptoms of cancer, which are not like skin cancer, things like that are obvious. Do you feel that there's a certain amount of stigma about some of the potential symptoms of colorectal cancer that would make people hesitant to talk about it or to get an intervention? Or do you find that that's a factor at all?
No, it's a major factor for pretty much every cancer you can think of for some reason or the other. You know, we're very aware that there is a stigma attached to the diagnosis and, in fact, divulging any information about cancers. That it just is the case in the majority of communities we've worked in. And we've worked extensively in rural communities to date. But I don't think it's anything peculiar about colorectal cancer or that region of the anatomy at all. It's simply stigma attached to cancers broadly. There may be a slightly added stigma to colorectal, but it's nothing unique.
Then digging down further into the education, which I agree with you is the absolute key to this, particularly in rural and deep rural environments. How do you propose to do that? And presumably you will be looking at a cancer holistic type approach, because trying to do something so specific, something like colorectal, would be very challenging when there's other, maybe perhaps more prevalent cancers. I'm not sure what the most prevalent in South Africa are, but breast cancer, for example, would be the most prevalent in Ireland, for example.
Yeah, interestingly, you know, we've been doing these trips to the Northern Cape with genetic testing, genetic counseling, and a surveillance body of people for the past 2 decades at least. And it is through working with the communities over this extensive period that we know that you've got to work holistically. So primarily with the healthcare workers, and I'm talking about, for example, the community health nurses in the first instance, who have a good understanding of communities. But increasingly, we realize we've got to be talking to schools. So as part of our outreach program is to reach to schools where the kids are, and to alert them about this particular phenomenon. But it's bigger than that. And it is a really good opportunity to talk general health. And in that regard, you know, we used to go alone as a clinical surveillance colonoscopy team of surgeons, gastroenterologists to the regional health centers. What started to happen is, in fact, we've got the National Department of Health, components of which actually accompany us on these outreach trips, and something like Pink Drive, which is interested in the gynae cancers, comes along with us, and we provide local awareness to a broader range of the community than just those individuals who are at risk for colorectal cancer. So to get to your point, I think it's really an opportunity to talk perhaps general health, but using the tip of the spear and speaking to the issues of hereditary cancers.
Yeah, I like that. And I also liked how you mentioned trying to target school children in terms of raising awareness, because if you have children and they're interacting with their parents and presumably with their grandparents and other generations or their families, they're going to be sensitive to these topics. They're going to be asking, have you thought about this? So I think targeting children, as long as it be done in an appropriate ethical way, could be a very powerful way of at least starting that discussion at a family level.
Absolutely, completely agreed, and that's the plan.
Thank you very much indeed. That was very interesting. So if there are no other questions, and I don't see any hands raised, Raj, thank you very much indeed. I hope that there'll be an opportunity to collaborate in the future. Our next presenter is Lorna, who's going to discuss towards an AI-based diagnosis of rheumatic heart disease, data annotation, and view classification.
Hello everyone, my name is Lorna Mugambi. I am a research intern at the Center for Data Science and Artificial Intelligence, and I'm also currently doing my master's at Dedan Kimathi University of Technology in Kenya. I co-authored a paper with Dr. Uzoka, who's a pediatric cardiologist, and Dr. Ashira Amaina. He's a senior lecturer at Dedan Kimathi University of Technology, and he's also the director at the Center for Data Science and Artificial Intelligence. The title of our paper is Towards AI-Based Diagnosis of Rheumatic Heart Disease, and in particular, at this stage, we're focusing on data annotation and the view classification. The World Health Organization has estimated that cardiovascular diseases are the leading cause of death in the world. In 2019, for example, it was estimated that 17.9 million people died from cardiovascular diseases, and this was a total of 32% of the global deaths in that year. Cardiovascular diseases affect people who live in low and middle income countries, and this is because they lack access to primary healthcare facilities, and therefore they lack access to early detection programs, and this leads to late detection in the cardiovascular diseases. And if a diagnosis is made too late, it may also lead to premature death. And therefore, it is important to detect these cardiovascular diseases early enough so that the treatment of the patients can begin. In this paper, we focused on rheumatic heart disease as one of the cardiovascular diseases. Rheumatic heart disease is a cardiovascular disease that is caused by permanent damage to the heart valves, and it is due to inflammation and scarring that is caused by repeat attacks of rheumatic fever. Rheumatic fever is a disease that mostly affects children, and it starts as a strep throat infection. So what happens is that there's an autoimmune body response to the strep throat infection, and this infection is caused by a group A streptococcal bacteria. Once we have these repeat attacks of rheumatic fever, then the valves might heal, and sometimes they may get inflamed or scar while they're healing, and therefore they do not they either thicken and they do not close properly, and this leads to a condition known as regurgitation, where the valves do not close well and we have backflow of blood. And it might also lead to stenosis, which is a condition where we have narrowing of valves and therefore we have restricted blood flow. And mostly the valves that are affected are the valves on the left of the heart. That's the mitral and the aortic valves. And eventually, if rheumatic heart disease becomes so severe, it may lead to atrial fibrillation, which is defined as heart murmurs, or it may also lead to heart failure. Studies have shown that when penicillin treatment is given to latent Rhd, we have decreased progression, And latent Rhd refers to a case where the individual is asymptomatic, but they've undergone an echocardiogram, and it shows that they have rheumatic disease, but they have no history of acute rheumatic fever. And there are some guidelines that were given by the World Heart Federation for Rhd in asymptomatic individuals. And some of these guidelines involve the thickness of the valves and the velocity and length of the regurgitant jet velocity in at least 2 views. So when an echocardiogram is done on a patient, there are different views that you can view the heart in. Some of them include the parasternal long axis, the parasternal short axis, the apic of chamber, the apic of F chamber, the subcostal view. There's so many, there are at least 12 views. And it has been seen that using the parasternal axis view, which I'm referring to as the Plaques view, and any other view with a color Doppler will give us 90% accuracy in diagnosing rheumatic heart disease. And therefore, our research objectives were developing a web application that will allow experts in echocardiography to label echocardiograms with relevant metadata so that we can diagnose rheumatic heart disease. Number 2, creating a machine learning ready data set of echocardiograms for training the Rhd diagnosis models. And number 3 will be training an echocardiogram view classifier. Those 3 were our objectives. Onto my next slide, we have the system architecture. Our web app was hosted on the Google Cloud platform. So we used the GCP app engine, and then we uploaded our data of echocardiograms, which was in form of images and videos, onto the cloud storage. We're able to display that on our web app that could be used by the experts. And then we used the metadata from the web app was saved on the GCP Cloud SQL. And then we are able to export a CSV file from this SQL database. And with this data, we are able to train our machine learning model and test this model and make predictions of the views that we have from these echocardiograms. And next up, I have a screenshot of the web app that we have. The first thing that you will see at the top is an image or a video of an echocardiogram. So the expert is able to play it or view the image. Then we have this annotation, the current annotation of the image or the video. And so this is either is this echo parasternal long axis view or not. I was only able to classify as those two views, and then do you have a regurgitant jet or not? And then the first field would be validating the current annotation that we have, and then the expert will give us the actual view of the echocardiogram. Then they tell us the thickness state of the valves. They'll tell us the condition or conditions, it might be more than one, that this patient has, and they'll also tell us the severity of the condition that they have. Then once they click this save button, all of this metadata is saved into a MySQL database, and then they're able to annotate the rest of the images using this next button. And the data that we started with comprises of 941 images and 852 videos. It was a total of 1,793. And we needed to pre-process this image due to computation. And because when you're training your machine learning model, you need a lot of data, and 1,793 was not going to do it. Therefore, from this data pipeline, we have the original RGB images that have patient details, and because we have to maintain patient confidentiality, we cropped the images to remove the patient details. And then we resized the images to an 80 by 60 from the original 784 by 562. And finally, we changed the images to grayscale. And as you can see throughout this process, we've reduced the size of the image, and we've also obtained 52,658 images, which are enough to train and test our machine learning model. And as I mentioned before, for the binary view classifier, the data that we used was not labeled by an expert. Therefore, we can only classify is the echocardiogram a Plaques view or is it not a Plaques view? And something to note is that our data was imbalanced. We had more not Plaques images and less Plaques images. Then there were 342 images that I could not classify as either Plaques or not Plaques. And then we performed a 70-30 split to generate the train and test data. And the 342 images that were unclear were used as test samples. Up next, we have results from our web app. These are results of the labeling done by experts of echocardiography. And from this, we can see that, for example, from the view of echoes as seen by an expert, we have a number of views, and this data can be used to train a multi-class view classifier as opposed to what we have, binary view classifier. We also have echocardiograms where the valves were seen as thick. And we also have different severities of RHD that were seen from the echocardiograms. There are some that were normal. There are some patients that had borderline rheumatic heart disease, and there are some patients that had definite rheumatic heart disease. And then there are also a couple of conditions that were seen in some of the patients. And as you can see also, some of the patients had more than one condition. And so far, we've been able to get 43 entries from the web app. You can understand because cardiologists' time is so important and they have so little time. And we are hoping we'll get more labeled data from the cardiologists. These are the results of the binary view classifier, where we use logistic regression. And the first image is an echocardiogram that was classified as not Plaques. And the second image, we have an echocardiogram that was classified as Plaques. Up next, we have evaluation metrics from our binary view classifier. We achieved an accuracy of 99.8%, precision of 99.7%, sensitivity of 99.5%, and specificity of 99.9%. And I'll say these are very good results. But as you can see on my right, from the confusion matrix, we had some echocardiograms that were not correctly classified. From this, I can conclude that the web application offers us a chance to get quality label data from experts or cardiologists, and this data will be really good for a machine learning model to train and test our multi-class bit classifier and also train our valve damage classifier. And these results can help the health practitioners give a fast and correct diagnosis for rheumatic heart disease. And the earlier that this diagnosis is made, the earlier the treatment will be administered for rheumatic heart disease. And this will help reduce premature mortality due to rheumatic heart disease in the low and middle income countries. I would like to thank Data Science Africa and Google for funding this research work. Thank you for your time and thank you for listening to me. And I invite any questions if you have any.
Thanks, Lorna. I enjoyed your presentation. We talked earlier today about the challenges associated with training data sets. So with echocardiograms, I'm sure it's even more complex in some degree, because presumably you need to have some sort of an appropriate mix of different ages, different genders, different progression of rheumatic heart disease, as well as clean images. So can you talk us through how critical that mix is, if at all? How you sourced the existing 941 images and 842 videos, and what you would recommend is needed, particularly for echocardiograms, to create meaningful, powerful training sets going forward. Thanks.
Thank you for that question. So as you mentioned,
sorry, Lorna, your sound is very low. Do you mind speaking closer to the mic or turning up your volume?
Okay. Am I audible now?
So I was saying earlier, dealing with echocardiogram data or health data is sometimes critical because we want to maintain patient confidentiality. And since we're dealing with rheumatic heart disease, most of our data is from children because they're mostly affected by rheumatic fever, and the rheumatic disease only manifests itself after a few years. So with the mix of the data, yes, we have different gender, but with the age, it might not be data from people beyond the teenage years. Then our source of data was from the pediatric cardiologists that we are working with. We haven't partnered with any others yet, but we're hoping we'll be able to work with more experts and be able to train on a little bit data that is diversified depending on the age, the gender, and also the location. Although we'll be doing this mostly in Africa because this disease affects people mostly in low and middle income countries.
That's true, but I'd recommend that you perhaps think wider, because I know that rheumatic heart disease is something that affects certain clusters in Latin America and in Asia as well. So there might be opportunities for collaboration where you could share data sets and therefore broaden what you have available to inform the tools you use both for training and for education purposes. Just a thought.
Okay, thank you.
Right, then just something I wanted to clarify, because I might have missed something. You
Okay.
talked about the binary view classifier used data that was not labeled by an expert.
Yes.
Okay, so
Yeah.
can you talk through, just for people who may not understand, what the implications of that are and how you overcame them?
Okay, so at the beginning, we did not have labels for the data, and we needed to train an algorithm on a simple idea like linear regression, because we needed to classify binarily between two different views. And I was able to sit with some of the experts, and we went through what an echocardiogram looks like and what different views would look like. And it was easy for me to label my data to train between two different views, which we use for the binary view classifier. But we've been getting more labels using the web application, and we'll also be doing the same with the labels that we've gotten from the experts. So it has been important for us to work with the experts in the field so that we get high quality labeled data.
I understand. So just to clarify, so the labels aren't simply, this is a male child of 8 years old with this progression of rheumatic fever. It's also a clinical diagnosis, essentially, of the image. Is that correct?
Yes, that's correct.
Perfect. Okay, no, that's very useful. Thank you. Right.
Okay,
Does
no
anybody have any other questions or comments for Lorna? If not, thank you very much. I warmly encourage you to continue what I think is very important work. Thank you very much, Lorna.
Thank you.
So the next presentation is by Gift, who's going to talk about tackling occupational nosocomial infection using Vitex-Medical assistant tool. Sorry about screwing that up.
Tackling occupational and nosocomial infection using Vitex-Medical assistant tool. Ladies and gentlemen, my name is Mugisha Gift Arnold. I'm a student and a co-presenter of the Vitex-Medical assistant tool. I feel so humbled presenting my team, headed by Dr. Professor Faith Michael Uzoka, a computer scientist at my Royal University, Mugisha Gift Arnold, Dr. Kingsley Atai, Dr. Barwaji A. Akwinwesi, Dr. Akputu, Dr. Samali, Dr. Peter, and old career, Christine Muhumza, Dr. Justin, Dr. Stephen Fashoto, Dr. Daniela Suko, Dr. Christy Akwao, Masi Edoho, Dr. Ifyok, Dr. Lucy, Dr. Andy S. Metzfula, and Goleti Cheyune. As I proceed, our table of contents is a classical one, starting with introduction, methodology, technology description, development, results, business benefits, and conclusion. Introduction, what motivated us? The increased rate and threat of hospital-acquired infections, especially the COVID-19 pandemic, and also the advent of antimicrobial resistant strains like MRSA, motivated us to come up with such a system where normal conventional ways of disinfection have been failing. We have an increased strain on the health workers due to the COVID-19 pandemic. This has led to a loss of livelihood during these seasons, and also poor patient health management, and especially this is endemic in African facilities. Our goal is to improve access to healthcare, reduce infections and medical errors, improve adherence to medication, and enhance the effectiveness and efficiency of hospitals and other long-term care facilities in meeting the clinical needs of inward patients. Our methodology started with idea generation, where we had a cardboard device. It went through a requirement analysis, and then we started off with a wooden device, which we actually presented at IST-Africa. And we have improved this into a sleek modern design that is undergoing evaluation. And soon, when we get the funds, we are ready to scale. Ladies and gentlemen, I would like to introduce to you the real Vitex-Medical device. Our device is a sleek, modern-looking design made out of almost 80% waste plastic bottles. We use plastic bottles to create a 3D filament, which we fed into a 3D printer, and then we came up with such a design. 20% of the system, 20% of the system is both metal and antimicrobial resistant plastic, which is also 3D printed. So our system can never be a magnet for pathogens since it self-sterilizes. The upper part indicated as 1 is our cutting-edge technology that uses FAR-UVC. It's complemented with a 1080 camera for patient monitoring. And then we have an artificial intelligence unit where we are coming up with new ways, innovative ways of transferring information from a practitioner to a patient by just the use of the mind. A patient just thinks and the transfer of information is made seamless. How important that can be, especially in patients who are bedridden with lethargy. The system has 2 touch screens for inputs and outputs. It has an amenity hold. The upper part is translucent. The lower part is opaque, prevent photo instability. The medication. The system has a support wheel for balance, and it has a charging area, so it can run both solar and electricity. That means it can even work in our normal village facilities. So developments, as I had earlier indicated, we are using cutting-edge materials like Practive, N1 plastic that disinfects the device body up to 99.9%, whether they are viral or maybe bacterial. So it also comes with a UVC engine, and this is in a package called germicidal module. And we have the amenity hold. The amenity hold contains drugs, masks for disinfection, and so on. Then we have the telepresence module that facilitates remote patient monitoring and remote patient care. Then we have the mobility module. The device can be able to move, and it provides a 360-degree coverage and transfer of supplies from one ward to another. The software acts as a threshold for patient data. So we have a repository in our software for patient data. So the power module comes with 2 batteries. One battery is for mobility, and another battery is for systems unit. So the system unit can be off while the mobility can be moving to just transfer materials, and vice versa. So it gives our system a very big competitive advantage when it comes to efficiency, especially energy. The results, ladies and gentlemen, here I can introduce to you the Vitex-Medical Assistant tool. This has been made here in Africa, particularly in Uganda. It has UV disinfection for UVC that is safe to work in congested rooms. It has medical waste carriage of up to 40 kilograms. It has a telepresence and remote patient consultation. It has remote patient vital monitoring. It has medical supply disinfection, such as masks, oxygen sensors, and it has an autonomous medical supply carriage. Our device also is autonomous, but can also be remotely controlled. And it has a patient record management with a repository of medical data. And finally, our system does predictive diagnosis, especially cancer diagnosis. So we are freeing up time for practitioners to narrow down to 3 or 2 specific illnesses, which really frees up the costs and also the time practitioners have to be around patients. The business benefits, ladies and gentlemen, our system is extremely user-friendly. Yeah. So it's cheap compared to our competition. Our neighbors in Rwanda procured robots from Belgium, and each cost $25,000. It had only telepresence and also patient monitoring. They had to go on to buy a disinfecting system that cost them $70,000. So in total, we have about $95,000. But ladies and gentlemen, our system will only cost $10,000 with more features and in one package. And remember, our device is also safe to use in congested hospitals. Since most of the hospitals in Uganda are congested. Actually, to be clear, our device can disinfect hands. So This will free up extra costs when it comes to refills of sanitizers. And it does this regardless of the antimicrobial resistance of these pathogens. So even if a pathogen is resistant, other chemicals of disinfection, our system can be able to inactivate it. It serves up to 50 patients and disinfects an average of 10 rooms per day and works for over 10 years. So in 10 years time, you will not have to buy normal conventional disinfectants for wide-scale sanitation. It also reduces the cost of personal protective gear as masks can be disinfected inside the device, and also because it's autonomous, it prevents practitioners from moving from one ward to another. Thus, no need of expending extra protective equipment. It also reduces the cost of medical services and reduces the cost associated with nosocomial infections. The use of the far UVC, as I've told you, reduces the advent of cataracts and cancer, making our system very, very safe. In conclusion, the processes and technologies and the benefits of the medical assistant tool Vitex have been discussed. And at this point, I would like to thank the organizers of the conference for this great opportunity for us to present to the whole world about Vitex. To the presenters and conference attendants, we are overwhelmingly happy for your time that you have given us to have this presented to you. May God bless you, and I remain Mugisha Gift Arnold, the co-presenter of Vitex Medical Assistant Tool. Thank you.
Thanks, Gift. Can you give us some insight in terms of what input you've received from medical practitioners in the co-design of the platform, and what feedback have you received to date based on the prototype? And then can you talk a little about what your target market within the healthcare ecosystem is? Thank you.
Thank you so much, sir. Okay, about the feedback from the hospitals, we took our old design, which was a wooden one that we actually presented during the IST-Africa 2017. Then when we took it to the hospitals, the practitioners advised us on some of the things like a self-sterilizing body, prevent transfer of infection from patients to practitioners. And then also they advised us on interconnectivity because our system was manual, it wasn't autonomous. So yeah. Then another question that you asked was about I don't know if you can remind me.
Of course, it was what specific target markets within the healthcare sector are you going after? You know, are you talking about trying to sterilize wards? Is it corridors? Is it surgery suites? What is the target audience?
Okay, thank you so much for the question. We are looking at surgical rooms, since we have tubings and so on that are not easily sterilized by chemicals. And then we are also looking at open wards in hospitals. Then maybe if we go on, we can actually go to hotels and so on, since our system can also disinfect anything, maybe environment and so on. But for now, we are limiting ourselves to hospital wards, normal hospital wards and surgical rooms.
Okay. So just something to think about. You may find lower barriers to entry targeting non-critical care environments, even within the healthcare sector, just in terms of building up trust and confidence, just something to think about. Does anybody else have any questions or comments for Gift? In which case, Gift, thank you very much indeed. And our last presenter today is Ernest, who's going to discuss enterprise medical imaging in the Global South, challenges and opportunities.
Friends, distinguished participants, ladies and gentlemen, my names are Ernest Obizulu. I'm a medical doctor and registrar in the Department of Radiology at the University Teaching Hospitals in Lusaka, Zambia. I'm going to present to you our work entitled Enterprise Medical Imaging in the Global South, Challenges and Opportunities. This work was prepared by myself and Dr. Lighton Peary from the Department of Library and Information Science at the University of Zambia. Ladies and gentlemen, radiology is a medical specialty that involves the use of clinical imaging for the diagnosis and treatment of clinical conditions. In a hospital setup, the Department of Radiology plays a pivotal role across all the generic disciplines of medicine, including pediatrics, internal medicine, surgery, and obstetrics and gynecology. Typically, in a hospital setup, the Department of Radiology will register patients that are referred after having been seen by physicians. When the patients present to the department, they are registered and imaged in various imaging modalities depending on the patient needs, and the captured images are stored in a server. A radiologist then accesses the images, analyzes them, interprets the findings, and prepares a detailed report, which is then fed back to the referring physician so that the radiological diagnosis can influence the management of the patient. Ladies and gentlemen, this is a basic skeleton of how a radiology department operates in a hospital in the modern era. Two fundamental challenges, however, affect the effectiveness and efficiency of the radiological services in the Global South, and these include a critical shortage of radiologists and the limited use of modern medical imaging practices. Our work focused on the potential solution to address the challenge of the limited use of modern medical imaging practices through the implementation of enterprise imaging. Enterprise imaging is a concept that includes techniques and workflows for acquiring, indexing, managing, storing, and analyzing clinical images. We had two objectives for our study: to highlight the challenges that adversely affect effective interpretation of medical images, and to explore the opportunities that are associated with the implementation and adoption of enterprise imaging strategies in order to enhance medical imaging interpretation in Zambia and the Global South at large. We used a mixed method approach where we took a case study at the university teaching hospitals and a meta-analysis. Specifically, we used the strengths, weaknesses, opportunities, and threats SWOT analysis through records analysis and personal observations. The meta-analysis that was conducted was based on enterprise medical imaging. We found out that there are 2,815 health facilities in Zambia, owned by the government, the defense forces, non-government organizations, and the private sector. But our work focused on the public health facilities in Zambia. Out of the 2,815 facilities, 151 are classified as hospitals under level 1, level 2, or level 3. And the majority of the hospitals are owned by the government and run through the Ministry of Health. It is worth noting that of all these facilities that are available in the country, as of the year 2020, only 9 qualified radiologists practiced in the public sector in Zambia, operating in only 5 facilities across only 3 provinces out of 10 in the country. Our case study at the university teaching hospitals reviewed the following workflow challenges: that there is no radiology information system or hospital information system. As a result, request forms for imaging examinations are inadequately prepared. There is repetitive entry of patient details at every step of the process. Final reports remain uncollected in the department and therefore are not feeding back to the requesting physicians to influence the management of the patients. And the preparation of annual returns in the department tends to be tedious because the process is manual. Secondly, there's no picture archiving and communication system. As a result, there's no systematic storage of images and reports. The reporting of the cases is done manually and therefore long. There is multiple registration of the same patient in the department as many times as the patient returns to the department for imaging examinations. And there's long report turnaround times. Ladies and gentlemen, time is of prime importance in the diagnosis of any health condition. The long report turnaround times at the University Teaching Hospital is twofold. Firstly, there are very few radiologists practicing at the hospitals, specifically only 2 qualified radiologists that are working against a heavy workload. In our review, we noted that, for example, in 2019, the annual returns revealed that there was a total of 92,600 imaging examinations that were conducted against only 2 radiologists that are available. We also noted that the majority of the modalities that are used in imaging are X-rays and ultrasound. This information agrees with what is available in literature across the world, that X-rays are the most commonly performed radiological examinations. Our meta-analysis generally revealed that there's one problem to do with the implementation of enterprise medical imaging, and that is the problem to do with the integration of various clinical imaging disciplines into a unified enterprise imaging strategy. And all this is due to the differences in the workflows for the different clinical imaging departments, differences in the image qualities and the standards that are used in imaging, problems to do with a lack of specific ontology and standard nomenclature, as well as medical, legal, and personal private concerns to do with imaging. Ladies and gentlemen, additionally, the Global South faces other challenges in the implementation of enterprise medical imaging. And these are a substantial cost that is involved to procure the platforms, as well as the ongoing requirement for continued investment to maintain the platforms. Secondly, there's also a requirement for a good information and communication technology service support, which is lacking in most of the Global South countries, and also the need for training of users and requirement for a good understanding of the complexities that are involved in enterprise imaging implementation. Our SWOT analysis at the University Teaching Hospitals revealed the following. Strengths. We noted that radiologists that are practicing are well trained from reputable institutions. We also noted that there is already an organized existing departmental stakeholders that are involved in clinical imaging. These various departments are already having their own administrators who are well established. They already operate on standard operating procedures, and although mainly manual, they have workflows in place which could be incorporated in an AI-centric ecosystem. They also have fairly equipped imaging ecosystems at all levels, operating with machines that are already compatible with the DICOM format, which is a requirement for enterprise imaging. And lastly, we also noted that there is already an ongoing mobilization of teleradiology equipment in order to link the various parts of the country to facilitate image sharing and reports transfer. Weaknesses. We noted that currently the different departments that encompass some form of clinical imaging are still operating independently and not integrated into the mainstream radiological imaging. We noted that there is continued use of old analog imaging systems that are not compatible with the DICOM format. We noted that there are variations in terms of the type of images that are acquired, including images that are acquired using light capturing devices. We also noted that there is poor equipment servicing, which leads to frequent and prolonged downtimes. And lastly, we also noted that there is lack of good ICT infrastructure across the country. Ladies and gentlemen, we noted the following opportunities that could be taken advantages of in the implementation of enterprise medical imaging at the university teaching hospitals. Firstly, there's already an ongoing development of an electronic health record system called Smart Care, which is currently being rolled out in the country. And there's also already an e-government service where the government is providing internet connectivity to various government departments and facilities. Threats. The following threats were noted: that even though internet connectivity is being facilitated in the different government departments and facilities, the internet connectivity is unreliable. And secondly, we also noted under the threats that there is still uncertainty over acceptability of integration of the various imaging departments into a unified enterprise imaging strategy. Ladies and gentlemen, with what I have presented, I would like to conclude by informing the participants that I presented to you a SWOT analysis that was conducted at the university teaching hospitals, which highlighted the challenges and opportunities of implementing a successful enterprise imaging strategy. We also presented to you a meta-analysis that was conducted to consolidate information on general and local challenges of enterprise imaging implementation at the university teaching hospitals and the Global South at large. I would like to mention that we are currently undertaking a pilot study to fully understand the imaging workflows that are employed in the public health facilities in Zambia. The expected outcome of this work is the possible automation of some of the workflows in order to enhance the efficiency of imaging in the country. We also have already in the pipeline plans of implementation of PACS and RIS systems, as well as development of machine learning models to aid radiologists, who are very few, in the interpretation of medical images. We also realize and note that there's still need for research, especially in the area to explore the possible automation of radiology report generation. Ladies and gentlemen, with those few words, I would like to end this presentation of enterprise medical imaging in the Global South, challenges and opportunities. I thank you.
Thanks, Ernest. In some respects, your presentation is quite horrifying insofar as 9 public sector radiologists in Zambia. What's the population of Zambia now?
Thank you so much. There hasn't been much of a change, and that was as it was reported in the year 2020. This is 2022, and we haven't had any changes in the statistics as regards.
No, I understand. I was just asking to clarify first. What's the current population of Zambia?
Correct. The current population of Zambia is, from the latest census that we had, is 18 million. But the last census was undertaken in the year 2010.
Okay.
So
And then, the obvious question to ask is, if there's 92,000 exams with 2 practicing radiologists, what's the turnaround time of those exams? And is some of the work being outsourced to the private sector? Are there private sector radiologists practicing as well?
Thank you for that question. Yes, the private sector is actively participating, but they have their own clientele. So about 70% of the population of Zambia relies on public health service. So you could understand from the statistics, you could interpret to say that about 12 million plus of the people of Zambia are reliant on public health services. And so those are the people that are reliant on the 9 radiologists, reported radiologists that are currently practicing in the country, excluding those that are actually reliant on or who could afford a public health service. So really that is the situation until up to this point.
And then what is the turnaround typically on an exam if there's only 2 radiologists and 92,000 exams?
So the turnaround time could range from, it's a quite wide range from a few hours to never being reported. So we do have some of the examinations that have been sitting, waiting to be reported, and probably a year or 2 have passed without a report coming out. And the other, forced strategy that is coming up is where we see radiographers whose job is simply to produce the images, becoming, involved in interpretation of some of the simple examinations to try and fit into the gap.
Yeah, I understand. And what efforts have been considered in terms of trying to introduce greater use of machine learning or AI or other techniques to do pre-processing of some of these images? Or that is not something that is on the horizon of the Ministry of Health at present?
So there are 2-pronged strategies that are currently, I think I can say, are being attempted. Firstly, to try and improve the numbers of radiologists, is that the government has introduced a postgraduate program to train doctors who are interested in radiology and locally within the country. And so they are recruited at sites where you have the few sites where radiologists are present, and they are being mentored in the specialty of radiology. Secondly, we have also a strategy where services of radiology are being outsourced from outside the country. For example, there is an understanding between the government and a private health or radiology company that is running in Zimbabwe, where some of the images are being forwarded for them to be interpreted, and the reports are sent back home.
Yeah, no, I understand. Thank you. Kutomo, you wanted to ask a question?
Yes, so I suppose this kind of relates to the latter part of your question and his Ernest's answer. So first of all, this was a very insightful presentation, so thank you very much for sharing it with us. My question is related to the weaknesses and the threats that result in SWOT analysis. In particular, I was very much interested in understanding whether there are any concrete solutions or plans that are being put in place, particularly with the new Dawn government, when it comes to overcoming this particular, the weaknesses and the threats that you talked about, especially when it comes to rural areas, because I imagine the situation there is a lot more dire than it would be in Lusaka, for instance, or other urban areas. I mean, one of the things that you mentioned was the fact that there are plans to introduce automation. I mean, how is that going to be done when there's so few radiologists to speak of, especially when you get into rural areas?
Thank you so much for that question. So we realized, in our meta-analysis that there seems to be very little, scant or no data at all that seems to indicate that there are other people who could be working in that area, especially when it comes to, when it relates to trying to mitigate the shortage of radiologists, especially in the rural areas. The few radiologists that are available, by the way, are all confined to what we call along the line of rail, and these are all urban cities. So we have a huge deficit in the rural areas, and this is where now it comes to the point that we are proposing some sort of a pilot study, which we have actually begun working on, to try and investigate the feasibility of implementing machine learning models to try and cover up the gap. And we are trying to do that, first of all, with chest x-rays, because we realize that they are the most performed radiological examinations, which are equally available in the rural areas. And these machine learning models could actually help to detect some of the conditions like pneumonia, so that diagnosis could be made in the periphery without needing a radiologist in place.
Thank you very much.
Thank you very much. Any other questions or comments for Ernest? In which case, Ernest, thank you very much. And I'm sure that there's many people in other countries who would be interested in similar analysis of neighboring countries as well. So this leads us to the end of day 2 of IST-Africa 2022. I'd like to thank you all again for making the eHealth sessions today so participatory, which is critical for effective knowledge sharing. Tomorrow, day 3, is focused around next generation technologies, starting with content technologies, and that's complemented by an invited speech from the South African Centre for the Fourth Industrial Revolution, which is discussing the take-up of Internet of Things by South African SMEs. So we look forward to seeing you again bright and bushy-tailed in the morning. Son Gafol and safe home. Thank you very much.